Okay. My name is Jeff. I'm the founder and co-developer of TDengine. I'm not sure you know time series data a lot. So let me spend just a very brief time to talk about time series data. Time series data is a series of time-stamped data, right? So we have lots of scenarios like IoT devices, sensors, meters, smart meters can generate all kinds of data. Those data are time-stamped data, and also like for Tesla, for lots of vehicles, they generate the data too. Okay, and another time series data scenario is DevOps, like each server, each virtual machine, each container, each microservice, they generate tons of data. They are all time-stamped data, and of course, financial market data is also time series data. Okay, but we already have lots of tools. Actually, it's time series database on the market to process those data. For example, the most popular one is InfluxDB, TimescaleDB, QuestDB. There's so many. So I'm an engineer. Okay, I used to write lots of code, and also even for the first version of TDengine, I spent 2 months at home to write the code for TDengine. Okay, so the big question is why we need a new time series database. There are already a bunch of them in the market. What's special for you? So I would like to spend more time to share on this part. If you check all those time database and also time series database, I think there are 4 things we need to mention. The first one is the tool should be developer friendly. For developer friendly, I list the 4 parts. First of all, the data ingestion should be very flexible because the IoT environment and also DevOps, the data schema is changed all the time. So schemaless must be supported. Okay, if you don't support the schemaless data ingestion, it's very hard for developers to use your tool. The second one is query language. Query language is very important. I think everybody knows SQL, and it's a very popular language. If you use a proprietary query language like KDB for financial markets, okay, they use their own query language. It takes time to learn, and also it makes the migration cost higher. And unfortunately, like for our most popular time series database, InfluxDB, they have their own query language. That's not developer friendly. Third one, you must be an open system. Okay, why we need an open system? Because in the time series database, there is a very old database there. It's based in San Francisco. It's OSI Soft. The product name is called PI. It's widely used in industry, but they are a closed system. It's very hard to get data out to machine learning for more analysis. Okay, so everybody want to use open source software like our TDengine open source. Okay, InfluxDB open source. Everybody open source. Without open source, I don't think for new projects nobody want to use your tool. Okay, the first point, you need to save the management efforts. For some tools, they are very good, but it takes you too much trouble to manage them. You always got a problem to manage those stuff, you know. So you need to reduce the management efforts. So that's from developer point of view. You need a very flexible data ingestion. You need to use SQL. You need to be open source. You need to reduce the management cost a lot. Okay. The second thing is because the number of devices grows every year. Okay. The data volume becomes bigger and bigger. You need a very scalable system. Everybody knows scalable. You can just add more CPUs, more memories, but we need horizontal scalable. Okay, Okay, I will talk about that more. Third thing is you need a very good performance. Okay, for like you need to be able to insert the data very quickly. You need to insert 1 million data points into your database. Okay, like for Oracle, for traditional database, they cannot do that. Okay, time series database can do that. Second thing is your query latency. You for some product, it always take a few minutes to get some query. Okay, that's very painful. If I could click the mouse, you can return the query result right away. It will be more welcome, right? Another thing is beyond the database. Lots of other components are needed for a modern data processing system. Back 20 years back, we just need a database plus some application. It can solve everything. But now it's not enough. We need a stream processing. We need caching. We need a data subscription. Okay, for the modern data processing. So that's why I think we need a new time series database. By the end of 2016, I decided to say those time series database on the market not good enough. Why I don't develop a new one? So I came up with the idea with the TDengine. Okay, so why we need a new one? What you can do for compared with the existing products on the market? I think we need to look more. We need to check more on time series data. Check more on characteristics of time series data. I listed them here. Say like data always have a timestamp. It's always structured. Data source is like a string. It's just like a video camera. The sensor always generates data every a few seconds or every a few minutes, right? And also data is rarely deleted or updated. But you do have a retention policy. Say, I want to keep the data just for 3 months or for half a year. Then you need to remove the data for me. Okay. And also another characteristic, very important one, is more write than read operation. Okay. For lots of tools, lots of tools like Cassandra, like HBase, okay, like MongoDB, they are like Kafka, Spark. They're all designed, developed by internet companies. Okay, they're widely used in internet applications. But for IoT scenarios, it's totally different because few people will check the raw data. Nobody view the raw data. But if you publish a tweet, okay, maybe 1 million people view your tweet. Okay, maybe 1 million people read your website. But for the smart meter, nobody look at your raw data. So more write than read operation. Okay, you need a very good ingestion rate. But okay, so for internet application, you need to do lots of optimization on read operation. Okay, and the number 7 is data rate is very stable for IoT devices because the sampling rate is almost constant. Like for example, you have 10 million smart meters in California. Every smart meter generates data every 15 minutes. Then for every day, you can generate 96 rows of data. Then you can calculate how much data can be generated by all smart meters in California. But for internet application, it's different. For holiday season, like Thanksgiving or Christmas, the e-commerce site, Amazon, the traffic will be 10 times higher than regular days, right? So, but IoT scenario, totally different. The data rate is very stable, okay? And the number 8 is you need real-time data computing because why we need to build IoT? We want to raise alarm. We want to do maintenance prediction. We need the real-time data, okay? But for internet, lots of big data platforms, they just provide batch analysis. Say, I want to get a profile for this customer on Amazon, or I want to get the profile for this person on Twitter. I can analyze the histories, but I don't need to give a real-time analysis. After I collect the data for more than 1 month or a few months, I can have a very good profile for this customer, right? So, but on IoT, it's totally different. You need to give real-time analysis, otherwise it's useless. I think your IoT device. Okay. Another one is for query. You always query the data in a time range. Like I just want to query the data for the past 1 hour or for the past 24 hours or the past months. Okay. I don't. For IoT scenarios, you never check all the history data because that's too big. Okay. The last thing is the data volume is really huge. Okay. Your system must be scalable. So by the end of 2016, I think if I take full advantage of those characteristics, I can design a very competitive product. Okay, that's why I started my own company. Okay, because I'm a developer. I like write code. Now, let me spend a few minutes to give a brief introduction about the TDengine. Then I talk about the internals inside the TDengine. Because I'm an engineer, I like to talk more about how to design this product. Maybe you can share, you can get more. Okay. Okay. Somebody always ask me a question. I will answer that after my presentation. Okay. Okay. First of all, we have very good performance. Why we have very good performance? Oh, okay. Let me. Why? Because our storage engine is designed by ourselves. We used all those characteristics of time series data. I'll talk about what's inside our storage engine. Because of our spatial purpose-built storage engine, our read-write performance is at least 10 times higher than general database. Compared with InfluxDB, we are still multiple times higher. Okay. And also, our data compression ratio is at least 5 times higher compared with a general database. Compared with the InfluxDB, we are like only 70% of the data storage size. Is a little bit better. Okay, I said here. Okay, for some queries, we are much faster than InfluxDB, much faster than general database. Okay, you guys, if you want to know more about testing, you can check our website to download our testing report. Another thing is scalable. Okay, the system, I said, you must be scalable. How to make the system scalable? It's easy because everybody know computer science, know divide and conquer. You need to divide the big data into small pieces. How to divide the data into small pieces? We divide in 2 dimensions. 1 dimension is based on time range. Like for each day, I put the data into 1 file in this direction, right? So of course, it's configurable. You can configure, say, 1 week for 1 file. Okay. Another dimension is to sharding. I put the data into different shards or different vnode. In TDengine, we call it virtual node. In Cassandra, they call it virtual node. Okay, we use the same concept like Cassandra. Okay, so each shard or each group contains a number of devices. Okay, like each shard contains 1 million smart meters. Then you divide the big data into small pieces. Once you divide the data into small pieces, of course you can analyze them. Okay, it's doable. Okay. Third thing I said, you must be developer friendly. So we support SQL. Okay, because we support SQL, we have JDBC driver. We have all those programming languages. It's very easy to use. Okay, just like the demo here, you can create a database demo, use demo, create a table, just like MySQL. Okay, insert data into a table, then select. Okay, easy, low learning curve, low migration cost. We are the one to support the SQL in the market. Another tool support the SQL on the market is QuestDB and TimesScale DB. Okay, the InfluxDB, Prometheus, they don't support SQL. Okay, KDB, they don't support SQL. Okay, another thing I want to talk is TDengine is not just a time series database. It's an all-in-one time series data platform because we provide caching, we provide message queue, we provide string computing, we provide the data subscription features. So for IoT platform or like for edge, especially for edge device, okay, you don't need to install Kafka, Redis, Spark, HBase to keep those tools anymore, right? So the complexity is highly reduced. Efficiency and performance are highly improved because we put all those features into one single software. Okay, it's really good for edge. Okay, so let me talk more on the edge. It's because for our TDengine installation package is only 3.4 megabytes. It's very, very small and low only other dependencies. Like some software, the installation package is very small, but when it runs, they still need to download many packages from the internet, right? So, but for us, the whole installation package is just 3.4 megabytes. Okay, no only other dependencies, and the minimum memory requirement is less than 16 megabytes, and it can run even on 32 Raspberry Pi. It can run. Okay, so it's a perfect solution for edge computing. For edge computing, sometimes people use SQLite. Okay, SQLite is a very popular one. It doesn't require much resources. Okay, the package and is smaller, and the memory requirement is even smaller than us. Okay, but they are SQLite is not a time series database. You need to write many code to handle some special features, like for example, data retention. You need to write code to remove the data. You need to write the code for downsampling, for interpolation, exploration, something like that, right? So you better use a time series database in edge side. Okay, now I finish a brief introduction. I really want to share with you all about the design, okay, inside. Why you have very good performance? Why your package is so small, still very good performance, right? You want to know why? So let me share with share this part. First of all, our number one innovation is data model. What's specific our data model is one table for one data connection point, or one sensor, or one device. You need to create one table. For example, in California, there are 10 million smart meters. Then you need to create 10 million tables. Okay. Let's look at the smart power meter. Okay. Each smart meter has a device ID, right? The 1001, 1002, 1003, and also the data connected is current, voltage, phase. Okay, for each data point, you always have a timestamp. Okay, and also for each device, there are some static attributes like static labels, like you have a location, you have a type. This smart meter is in San Jose, another smart meter in Palo Alto, another one is Cupertino. Something like that, right? And also each smart meter maybe have different model, different type. So if you use MySQL or any other general database to save those data, you always design a table like this: device ID, timestamp, and the current voltage phase, location type, and save rows by rows, right? But if you look at this, the data, if you look at the table, because network latency is different for each device, even the devices are synced by GPS, but the data points won't arrive at the server in the order. Okay, so the data points will be out of order. And also the second thing is for each device, their data characteristics is different because, for example, voltage, some device voltage is 220, some device is 110. You mix them together. And also for static table, you save them repeatedly. That's a cost of storage. But if we put one table for one data connection point, okay, look at this, then I create 3 tables for 3 devices. Look at this. Then I don't need to save device ID anymore. Just save them one time. I save those labels, like California San Jose, just one time. And also time stamp will be in the order because also the network latency is different for each device, but the relative order for one device won't be changed, right? So it's in the order automatically. Then the data insert operation becomes an appending operation. If you append a record into the table, it's very efficient. And another one is the characteristics of the data itself is very clear. Like for voltage, it's always fluctuate around 220. The current fluctuate around 3.1. Then, you will get lots of benefits. Okay, it's very easy to compress. Okay, now at least put one table for one device, you get a very good data ingestion rate because it's a appending operation. Okay, how to improve the query speed? Okay, now we have another strategy. We store the data block by block. Okay, each block contains a number of records. Okay, and also for each block, I have a pre-calculation, like the maximum, minimum, the sum, the count is already saved at the head of the block. Okay, and also for IoT query, for IoT devices, if you run a query, you always run a query for a time range. You want to read a specific data point. Looks like a regular database. For regular database, you want to check Jeff's birthday, for example, Jeff's location, just one record. But for IoT devices, you always check the data for the past 1 hour or for the past 5 minutes. You always have a number of data points. So if I save data points in a block, one IO operation, I can read out many data points. It will be very, very efficient. Okay, so the query latency is much smaller. Okay, look at another slide. And for each block, we save the data in column by column. If for the regular database, they save the data rows by rows. Look at here, it's rows by rows, right? One row by one row by row. But we save the data in column by column. We save the data for timestamp first, then we save current, then we save voltage, then we save phase. For each column, the data type is different. Then we can use different compression algorithm to improve the compression ratio, right? And the big advantage is if column-based storage, because like for voltage, it always fluctuates around 220. Then we calculate the delta or the difference first. Then we don't need to use 8 bytes or 16 bytes to save the voltage at all. Then we can improve the compression ratio much higher. You get a much higher compression ratio by column-based storage. Okay, and also many databases. Okay, like for example, ClickHouse, they also use column-based storage, but our compression ratio is still higher because one table for one device, and also the data I already explained multiple times. The data is almost the same. Then it's much easier to compress. Okay, so let me summarize. Our strategy is one table for one data connection point, and the records are always stored block by block and continuous inside the block. It's a column-based storage for each block. Then we can ensure read-write efficiency of a single device is the best. I don't think you can come up with the idea to be the one table for one device. Okay, that's the most simple way and the most efficient way to read-write data for one single device. Okay, let me talk about more about there are some other things for IoT. Okay, because there are many data connection points for the same type. Like for I talked about I will talk about again. Like for California, there may be more than 10 million smart meters, right? Like in China, for one province, there maybe have 100 million smart meters. Okay, and also the same type of devices always want to be aggregated. Because, for example, I want to aggregate all those smart meters in San Jose. I want to find the total power consumed by San Jose, right? I want to aggregate all those smart meters in our office building. Maybe there are 100 smart meters in our office building. I want to calculate what's the total power, right? So you need aggregation. And also, you need a multi-dimensional analysis, okay? But when you do the modeling, you don't know which dimension you want to analyze. For example, for the vehicle analysis, maybe the model make a big difference. Is Tesla Model 3 or the latest Tesla model, right? And also maybe depends on the driver's age, depends on the driver's sex, depends on the driver's location. You can have different analysis, that's different dimension, but you don't know those dimensions at the beginning. So you need to add more dimensions. So for my design, one table, one device, okay, then brings so much technical challenges because the number of tables is huge. It's difficult to manage and difficult to aggregate. Okay, how do you solve this problem? Then come up with our second innovation. We give a new concept, it's called the soup table. It provides an efficient way to aggregate the data for devices. Okay, what is soup table? It's just a category or a certain type of devices. Okay, to describe a soup table, like let me speed up. Just give an example. Okay, for example, I always like to use smart meters. Okay, because it's very straightforward. Okay, for smart meters, okay, I can create a soup table for the smart power meter. Okay, so for this category. Okay, so I define a table, just create a table smart meter. There is timestamp, current, voltage, phase, but compared with the regular database, I have an extension called tags. Tags is location type. And then for each smart meter, I use the soup table as a template to create the tables. For example, I create table T1 using smart meter, give a type, California, San Jose, then another one, California, Palo Alto. Okay, you can create those table for each device based on the soup table. So soup table is just a template. Okay, and also compared with regular database, each table has tags. Like MySQL data for Oracle, MySQL database, they don't have tags. Okay, concept. But here we add tags for each table. Now, if we want to check the query for aggregation, then it becomes very simple. For example, I want to query the average voltage and maximum current of all smart meters in San Jose. It's very simple query on SQL. Select average max from soup table instead of a specific smart meter. But I put location, the field here. Okay, so it's very easy. Query the average voltage of type 1 smart meter in whole California, then the same. So soup table can be queried like ordinary people, but you can specify the field of labels. And also you can have more than 128 labels And each label actually is an analysis dimension. Okay, labels can be added, deleted, and updated after the data modeling. Also, like I want to add a new label, it's easy. You can just add, no problem. Okay, and also each label can be a tree structure, which can narrow the search scope. For example, California, San Jose, I can just use California, right? So you can narrow your scope. It's a tree structure. It's hierarchy. Okay. And also from technology, okay, from engineering, we also have some innovation for the label storage. We always label is stored totally separate. Label data is stored, completed, separated from time series data. Okay, so time series data and the label data are stored in different location. They are separated. They are not mixed together. Okay, and also we use just KV storage to store the label. Okay, and but the data volume for label is small because for each device or for each data connection point, just one label record. Okay. And also label records are stored together and have index. We build the index. Okay, there's so many advantages. Let me just give you the flow. Okay, for example, I want to. There are more than 10 million smart meters in California. I just want to query the smart meters in San Jose. Then how to do? The app send a query command to the engine. Then it put say, please find out those smart meters in California, San Jose. It goes to our TAG data, okay, label data. It give you the list. Then it give you the list. Say, oh, you have 10,000 smart meters in San Jose. I return the list to you. Then TDengine goes to time series data to aggregate the data for those 10,000 smart meters San Jose there. Okay, so by this way, we reduce the data set small a lot. We reduce the data set for aggregation to very small set because we do field first. Okay, so in fact, the TAG data is dimension table, and the time series data is just facts table. Okay, or from another perspective, the design of the SOAP table is a two-level index structure. The first level index is a label used to field data connection points. The second index is timestamp used to filter the connected time series data. So it's a two-level index. The first level index is just for devices. I want to fill out the devices, right? Like for fill out the devices in San Jose. Okay. Then second index is timestamp. Okay. So let me summarize. So with SOAP table, we can reduce label storage space significantly. We can improve aggregation efficiency of devices significantly. And also we can enable convenient multi-dimensional analysis. Okay. So that's all in very good parts. Because I already spent more time. I'll give you some slides. Of course, everybody know high reliability is very important. We just use WL to provide reliability. So if your computer crash, we can still recover your data. And another good thing I want to share is multi-level storage. Okay, because we can store the hard data in memory. Then after 1 hour, we move the data into SSD. SSD is performance is very good. Then after 1 week, maybe 10 days, we can move the data into local hard drive. Then after 6 months, we can move the data to S3 storage. It's very, very cheap, right? So it can save your total storage cost a lot. Okay, why we can do this? Because it's time series data. We chop data based on time range. Okay, every block only is for a time range. Okay, it's very easy to do that, but it's hard for internet application. Okay, I don't need okay, let me still spend a few minutes on this. Our TDengine architecture is a distributed system. This distributed system is just like any other NoSQL database, like a Cassandra, like a MongoDB, like a Redis. Okay, almost the same. Okay, each node has some shards. Like here, we have V2, V7, V6, V8, and then the same shard, like V2, on different nodes can be a node group, okay, or shard group. So to provide the high availability, if one node crash, other two nodes are still working, then the whole system can still provide the service to provide the high availability. Okay, and also we have management node. Every node reports their status to management node, and also management node is called meta node too. They store some metadata. Like for example, the super table definition and also the nodes information, they are all in M node. Okay, the typical process is very simple. I don't want to. Okay, let me talk about a little bit about the writing process. It's just like only other NoSQL database. You write, then write the data into log first, write a head log, then forward the data to other peers. To provide a high availability, then write to memory. Once you write to memory, then you can send the IKE back to application. Say, I write the data successfully. Once you give the IKE to the app, the data always stored, always saved successfully. You can always retrieve, no matter what happened. Okay, looks like the whole process looks like the same as any other NoSQL database, but the difference for memory writing. Inside the memory, we keep a queue for each device or each data connection point. If you have 10 million devices, then I have 10 million queues in my memory. The queue is a first in, first out queue. Okay, so I always keep the latest data in memory. So you can always retrieve the latest data quickly, okay? And also, when you write the data into file, there's some difference, okay? Because we chop the file based on time range. Each file only saves the data for 1 day, okay? All those time series database use this strategy. They always chop the data based on time interval, time range, okay? Like 1 day for 1 file, 1 week for 1 file, the same. So with this strategy, it's very easy to locate where is your data. Once you tell me your query time range, I can locate the data right away. So in this file or another file, or is in memory, because I can calculate, okay? Easy, okay. I can skip this part. There's still some other good parts about the TDengine, okay. For example, very easy for the downsampling, for the roll up. I want to calculate the average temperature for every 5 minutes, okay. So I want to, okay, even I want to calculate the average temperature every 5 minutes for the whole California, right? You can do that for each device, very easy for roll up, okay? And another very good feature is and also this feature is very important for IoT scenarios. It's called the continuous query, okay? So let me just give you the example. Calculate the average temperature of California for the past 5 minutes, for every minute. Every minute, I want you to calculate the average temperature for the past 5 minutes, right? So then you just need to write down SQL like this. We provide 2 extension keywords. One is called interval. It's the window size, like 5 minutes. Or then the sliding window. So what's your rate? What's your how soon you want to calculate? Every 1 minute you want to calculate. Okay, and also you can put the continuous query result into a table. Okay, for example, like a table D1. Okay, you can do that very easily. Another thing is we can do data subscription, because data subscription is very, very important for IoT platform. because the data won't be consumed by just one single application. Maybe the data can be consumed by multiple applications. Everybody want to get notified once you have new data. So just like Kafka, but compared with Kafka, we have something new. We can filter the data because we have a schema. We know what's your structure of your data. So like, for example, I want to just subscribe the data in San Jose. Okay, I just want to subscribe for devices with voltage higher than 2020. Okay, I don't want to subscribe devices with voltage less than 100, for example. You can put all those filters in your subscription. It makes more efficient. Okay, caching. Okay, caching is very important for IoT. Okay, because everybody always want to know the latest status of a device. Okay, for example, like for the vehicles, okay, connected vehicles, I want to know for the Uber. Okay, I want to know the current location for this vehicle, for this Uber. I want to for the delivery, like for Daishido, I want to know the delivery guy, where is his current location. I want to check. So for us, it's very simple. We just provide an SQL function, last row. It can return those stuff right away. So it's very important feature. Okay. Okay. My last slide. We have lots of beautiful features, very good features, but we open source our software. For single edition, we open source in 2019, but for cluster edition, we open source in 2020. InfluxDB open source the software long time back, but only for single node. The cluster edition is closed, is a lot of open source. Okay, up till now we already have 18,000 stars on GitHub. Just less than 3 years, we already have more than 18,000 stars. We have already more than 4,500 forks. And also we have many developers submitted issues for us. Okay, so I'm very proud of this because we lots of developers like us. And also for every day, there are more than 1,000 clones on GitHub. And also every day, there are over 200 new instances running in the whole world. Okay, in Europe, in US. Okay, everywhere. You even don't know. Sometimes I have found very strange. Even in Vietnam, many people are using our product. In Japan, some people download us. Yesterday, I found some people from Germany download our software too, right? So that's the beauty. That's a very beautiful part for open source. Okay. You can reach, it's accessible by all those developers in the world. And also, I hope you can check our website and just try. It's very easy. And also, that's my personal information. I always stay on Twitter and LinkedIn. You can follow me on LinkedIn or follow me on Twitter. And also, you can, if you really have interest on our TDengine, you can join our Discord. So I can answer all those questions. Okay. Thanks. I think.
Okay. Thank you, Jeff. Perfect timing. So we have a few questions with the remaining time. There's a question actually about what does it mean where about the data rate is pretty stable.
Yeah, that's a very good question, Patrick. So why there is a very stable data rate? Because for IoT, the sampling rate is almost always constant. Like for smart meters, they always generate a data point every 50 minutes. Then if you have 1 minute smart meters, every 50 minutes data rate, you can calculate. Okay, a lot like internet connection, a lot like internet application, like for example, for Amazon. In the holiday season, the traffic, you cannot predict, maybe 10 times or maybe 50 times higher. I live in Beijing for a long time. Every Double 11 holiday in China, the Alibaba's website is 100 times higher traffic. Yeah. So I mean, for IoT is pretty stable. Okay. The second question.
Yeah. What types of memory does TDengine work with?
Note that there's some device allow include. Oh, I can work with only kinds of memory. Okay, no problem. TDengine can work with only kinds of memory. No only problem. Okay. Third question was asked by Patrick. What does it mean to say that each block comes with pre-calculation? Very good question. Okay. Because for each analysis for IoT, you always want to check. Like sometimes you want to do some very simple statistics. Say I want to find out what's the maximum voltage for the past 1 hour. I want to find out what's the average voltage for the past hour, right? But for the past 1 hour, maybe you already have 10,000 data records, 10,000 data points. To get the maximum or minimum or even the average, you need to scan the data to find out. But for each block, if you have a pre-calculation, I don't need to scan. I know for this block, it's already there. I don't need to scan the raw data. So the query becomes much, much faster. I can return the result to you right away. It's a good strategy to reduce the query latency. Most modern databases has this feature, not only us, okay? Like InfluxDB has this feature too. Lots of database has this feature. Yeah. Okay. More questions?
Any other questions? And did for Patrick and Tom, did Jeff answer your question correctly?
Yes, yes. He basically said it works with any type of memory. Thank you.
Oh yeah. Okay, great. So
okay. The presentation is recorded, and the recording will be posted on the Consumer Technology website shortly, probably in a few days, because we are volunteers, so we have to edit it a little bit before we post it back up. And then you have Jeff's contact information on this slide. If you have further questions, you can contact Jeff directly. And then thank you. Is there anything else, Jeff? Do you want to close before we end the recording?
Yeah, thank you all for joining this webinar. Please follow me on LinkedIn or tweet if you have any questions, because I'm an engineer. I really like to get feedback on our product. And also because I built this product by myself, I'm very proud, you know. So I always like to, you can give me all those challenges. I like to answer, okay?
Jeff, it's a very interesting presentation.
Pardon me, Olga?
It was very good presentation. I have a lot of questions actually for Jeff, for my little project.
Oh, one more question.
Okay, so so I asked the people put in the Q&A. So why don't you go ahead, Olga?
No, not now. It's I'll do it offline. It's one which I work with the government on government program on.
Okay, so
it's interesting.
Yeah, so you have Jeff's contact. You can always ask Jeff afterwards.
Thank you very much.
We're coming up to the end of our meeting. So so I'd like to thank everyone for attending this meeting, and please go check out our website for the posting in a few days, and also for any new events coming up.
Okay, thanks.